Welcome to another foundational lesson. In this lesson, I'm going to tell you about numeric sets. Now, as the name implies, a numeric set is just a set that contains a bunch of numbers. Historically, our definition of number has actually grown quite a lot as we've learnt new problems and tried to actually solve them. Now, since some numbers are actually larger than other numbers, it's natural for us to draw numbers on a number line. If you were to pick 2 points on a number line, the number on the left of the number line is going to be smaller than the number on the right. The first numbers people ever invented were the natural numbers, and in a sense the natural numbers are really just counting numbers. One of the earliest uses for numbers was to just count things. Like imagine you had this cow over here, and then you wanted to count 1 cow plus another 2 cows. Well, you just have 3 cows in total. In fact, people have been counting for so long that we managed to dig up tokens from over 3000 BCE that looked a little bit like this. These were found in modern-day Iraq and are believed to be from the ancient Gersu civilization. This one on the left indicates 1 sheep, and this one on the right indicates 1 jar of oil. This all just shows that we've been counting for a really long time. In fact, tally marks have been discovered from tens of thousands of years ago, and numerals that indicate whole numbers have also been found. But in any sense, this shows you why we call the natural numbers natural. In a sense, we already know what it means to count things, and therefore the natural numbers contain all of the counting numbers. So we would say that the natural numbers is the set of numbers 1, 2, 3, 4, and so on. Usually, we indicate numeric sets with one of these fancy letters. So I've drawn the set of natural numbers in this Venn diagram over here. And we start with just 2 examples. For example, the numbers 3 and 6 are natural numbers, and we can place them directly onto our number line. Now, depending on who you ask, some people allow the number 0 to actually be part of the natural numbers, and some people don't. Now, the argument can be made that 0 isn't really a number, and for that reason, we didn't actually see 0 appear for quite a long time. One of the earliest usages of the number 0 occurred in the Khmer Empire. I may be saying that wrong, but the general idea is that this symbol over here represented 605, and this little dot over here represented the number 0. Now, people were totally content with the natural numbers for a really long time. But of course, you learnt about a lot of different types of numbers as well. Aside from the natural numbers, you can extend the numbers to include negative numbers as well. But negative numbers posed a huge challenge for a lot of people, for one really simple reason. I want you to imagine that I started off with 3 cows, and then I sold 5 of them. How many cows do I have now? So technically, if you start with 3 cows and you sell 5 of them, well, you have to invent 2 cows to somehow give to the person you sold it to. And for this reason, the question 3 minus 5 produced an answer that many mathematicians for a really long time considered to be completely crazy. That is, of course, until people realized that if you had 3 cows and sold 5, then you technically owe somebody 2 cows, and therefore negative numbers became super important to help deal with the problem of debt. Now these days, negative numbers are so ingrained into our society that most people don't even bat an eye about them. But when I was really young and I first learnt about them, I found it totally crazy to have numbers that were actually negative. Despite this, there was lots of evidence historically that people have been using negative numbers for a long time. This counting stick over here was found in 100 BCE in ancient China. So therefore, this causes us to expand our set to include all whole numbers, including the negative numbers. When we extend the natural numbers to include all whole numbers, we call these the integers. So therefore, as we made the jump to include the number 0 and the number -1, we needed to make the jump to include a whole bunch of numbers that didn't exist inside of the natural numbers. So for example, 0 is not a natural number, at least by our definition, and neither is -1 or any other negative number. Now because 0 and -2 don't belong inside the natural numbers, we have to draw them outside. But that means we need to extend our set to include these numbers as well, and that's what the integers are supposed to do. Now, just as we did before, we can also map these numbers directly to the number line below. Now, it's important to realize that the natural numbers are actually a subset of the integers. They belong completely inside the integers. And that means every single natural number must also be an integer, but not every single integer is a natural number. So for example, 6 is both a natural number and an integer because it's inside both of those sets. But -2 is not a natural number, but it is an integer. Now, of course, people used whole numbers for a really long time, and whole numbers were okay in many situations. But there is actually a slight problem when you're only allowed to use whole numbers. So here's a problem that happened basically all the time. I want you to imagine 3 people went out for a hard day's work, and after the day was through, they earned themselves 7 gold coins. Now they want to divide these coins up amongst themselves. So the first takes these 2 coins, the second takes these, and then the third takes these 2. But then we have this 1 coin left over. And who gets that? Now, the first idea would be to break this coin up into thirds. But in most societies, destroying currency is actually illegal. So to solve this problem, many societies adopted fractional currencies and made the smallest unit so small that most people would never bother fighting about it. However, for many things, it is actually totally possible to split the thing up into parts. For example, if this coin was actually a pie, you could easily cut the pie into thirds and give a third to each person. And then at this point, people started to realize that fractions are actually numbers as well. And therefore, many people started to adopt them into a set called the rational numbers. Now, just like the integers contain all of the natural numbers, the rational numbers also contain all of the natural numbers and the integers. Now these numbers don't live inside of the integers. 9 3/4, -1/3, 0.23 and 0.5, none of them are actually integers. They're parts of a whole instead. And therefore, they also prompt us to extend our number system to include these rational numbers. And just as we did before, we can directly map these rational numbers to the number line as well. Now, just as before, the rational numbers are a superset of the integers, and therefore every integer is a rational number, but not every rational number is an integer, nor is it a natural number. Now, the earliest use of rational numbers actually comes from the ancient Egyptians, where they would write this symbol to indicate 1/3, and you can kind of see the 1 and the 3 at the bottom. And this symbol over here would indicate 1/10. Their system was a bit different to ours, but it is pretty similar in some ways as well. But as far as defining the rational numbers is concerned, there are actually a few ways that you could go about it. So the first way to define a rational number is by saying that any rational number can be written as a over b, where a and b are 2 coprime integers. The word coprime is a little bit tricky here, but it just means that they have no common factors. For example, 3 over 4 is one possible rational number, because 3 and 4 have no common factors. But you'd never write 6 on 8, because 6 and 8 can both be divided by 2 to bring you back to 3 on 4. But then another way to define them is by saying that a rational number is basically any number that has a pattern in its decimals. So for example, if you wrote 73 over 26 out as a decimal, you would get 2.8076923. But then this 076923 part will continually repeat. So it's 2.8076923076923 and so on. But as you probably guessed, it is totally possible to actually write out numbers that do not have patterns in their decimals like this. And we call those numbers real numbers. It was actually the ancient Greeks who first figured out that there are some numbers that are not rational. And the way they did this is actually really simple. I want you to just imagine that they constructed a triangle with sides of 1 unit and with a right angle over here. After this, we just take this point up here and project it down to the number line by following a circle, we do this by actually taking a string and then tracing it out like this. This triangle was constructed so that the base and the height were identical. If this was 1 unit, then this must also be 1 unit. Then this diagonal length over here, which we projected down here, would be called today the square root of 2. Now, proving to you that the square root of 2 cannot be written as a rational number is a little bit outside the scope of this video, but I will make another video on it and you can watch that if you're interested. But that immediately tells us that if you were to write out the decimals of the square root of 2, no matter how many decimals you expand, you will never find a pattern like this one over here. And that's what it means to be irrational. It turns out that the square root of 2 is not the only number that we can't write as a rational number. There are others like the square root of 7, and the number we call e, and another number that we call pi. Therefore, there exists a set outside of the rational numbers that we're going to call the real numbers. So therefore, the best definition I can give you for the real numbers is that it's going to include every single number on the number line, whether or not it is rational. And therefore, all of these numbers must have a place on the number line. Let me actually put them where they belong. Now, you'll very likely get very familiar with all 4 of these numbers that I've put on, but I've just put them in their approximate place on the number line. One of these numbers is actually particularly famous, this number pi. There's actually a pi day, and people try to outdo each other, memorizing as many digits as they can of this number. In fact, to test how fast different computers are, some people write programs to generate literally billions of digits of pi in an effort to show how quickly they can generate digits. These days we've generated more than 1 billion digits, and there are actually no patterns in those digits. Now I use the word pattern a little bit loosely, but what I mean is that at no point will you be able to say this is the last digit I need, because there is no way that you could figure out all of the digits in one go. With a rational number you could easily figure out the millionth digit, but with a number like pi, it's a little bit trickier. Another thing to say is that all of these sets are actually infinite sets, and I have definitely not drawn all of the numbers that belong in them. There are so many of them that I couldn't possibly draw them all. Now at this point you might feel like this is where our definition of number stops. But it turns out that there are actually many more possible numeric sets out there that are actually outside of the real numbers. I won't say anything else about them for now, other than to say that they exist. If you continue studying mathematics, you'll see many other numeric sets, and you'll see exactly why we bothered to define them. Every time we come up with a new problem, a new numeric set may actually make that problem a fair bit easier to solve. But now I'd just like to summarize everything. A numeric set is basically just a set that contains numbers. But our definition of number has changed throughout the years. A natural number is the simplest number, and natural numbers are just used for counting. At some point we realized that the natural numbers were not adequate, and the number 0 needed to be invented, and so did the negative numbers. So then at that point, we decided to invent the integers. While trying to solve the problem of dividing a whole into parts, eventually we needed to define the rational numbers, which are outside of the integers and the natural numbers. There are 2 equally good definitions for the rational numbers. You can think of them as a pair of integers a over b, where a and b are 2 coprime numbers. Coprime numbers are just 2 numbers with no common factors. Or you can think of them as decimals, where there are actually patterns in the decimal expansion. So for example, 2.8076923, 0.76923, 0.76923, and so on. But then to finish things off, we said that not every number in the world is a rational number. There are some numbers out there that we call real numbers, and those are just numbers that may or may not be rational. The only thing we can really say about the real numbers is that they do belong somewhere on the number line. Learning about the numeric sets is actually a really important point on your mathematical journey. When you actually learn about the numeric sets, you're going to start to take any problem, whether it be in terms of cows or coins or anything, and represent them in terms of numeric sets. The reason we do this is because we can actually perform operations on the numbers inside of these numeric sets. Learning about the operations that we apply to these different numbers and learning what they do and how they work allows you to solve a whole huge range of problems that you can't even imagine solving right now. Now there is actually quite a lot more to say about numeric sets, So I invite you to join me in the next few lessons, where we'll talk about them some more and show you some of their properties. But for now, that's all I'd like to say on numeric sets. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.